Buenos dias. It's a pleasure to be in Madrid. And today I'd like to talk about how can we break the chain of infection. For example, by using, if this works. This way. Yeah. For example, by using our old friend copper to break the chain. So just some very brief data. This is some old data from the USA, which Michael Schmidt might comment on later. Going into a hospital is a very dangerous thing to do. The longer you stay, the greater the risk of infection. So up to 2 million people acquire an infection each year in the USA when they go into a hospital. 100,000 will die, and it costs a lot of money. At least $47 billion. It's very expensive to treat each patient, and the World Health Organization suggests it costs at least $80 billion and includes at least 7 million people. And these are quite old figures. We're seeing an increasing trend in the rate of infections and also increasing antimicrobial drug resistance. Now, if we talk about Europe, over 4 million patients are affected each year when they go into a hospital in Europe. This costs an extra 16 million days in hospital, at least 7 billion euros in direct costs, 37,000 deaths directly caused by a healthcare acquired infection, and an additional 110,000 deaths where the hospital acquired infection is a contributing factor. It's recognized now by many governments around the world that 80% of all infections in hospitals are spread by touch. And this, of course, immediately brings into question, what do we touch in a hospital? Door handles, push plates, for example. There have been various clinical trials around the world now where they look at how efficiently staff clean their hands, wash their hands. And it's not very good. Male consultants are poorer than female nurses. Women are hygienically cleaner, and their hand washing is not good. We also know that alcohol rubs are not good because they do not kill norovirus or spores. Now, when we actually look at the infection rates in the European Union, if we look at the percentage of hospitalized patients, between 5 and 6% of people who go into a hospital acquire a hospital infection. This is over 6% in the European Union and almost 6% in England and Wales. But particularly if we look at the intensive care units, they're the patients. We have over 23% of the patients in intensive care acquire an infection. In the UK, it's about 20%. But very worrying is that in some European countries, this infection rate can be as high as 51% in intensive care units. So this is very dangerous. Now, the problem is humans are very tactile. We touch surfaces repeatedly. We touch our faces repeatedly. And to remind you, 80% of infectious diseases are transferred by touch. Now, the problem is how well can we clean a surface? So this is a surface which has been deliberately so this is stainless steel. So to the eye, it looks like a mirror surface. But if we inoculate bacteria onto there and then try and clean, so this surface has been professionally cleaned, you'll see the bacteria which survive in the scratches or draw marks of the metal that you cannot see by eye. So stainless steel is not easy to clean as claimed, and therefore we have a risk of cross-contamination if we touch that surface and then go and touch a patient or touch another surface. We have problems with terminal cleaning. So this is what happens after a patient has left a ward or a confined area. cleaning staff will go in and they will deep clean. But in this particular study that was done in the UK, they were interested in what happens with MRSA, methicillin-resistant Staphylococcus aureus. And 74% of the ward environments were positive for MRSA before the deep clean, and still 66% were positive after the deep clean. So this suggests that we need more passive preventative measures to reduce MRSA populations on touch surfaces in hospitals. And in fact, you might argue also in food processing factories, public transport systems. Now, another issue is we have the rise of the superbugs, hence the Superman sign here. So these are things like MRSA, VRE, vancomycin-resistant enterococci, Clostridium difficile spores. But we also have the emergence of the ESBL bacteria. This stands for extended spectrum beta-lactamase producers. So this includes E. coli, Pseudomonas, Acinetobacter baumannii. But in particular, we have emerging classes such as Klebsiella pneumoniae, which can produce a carbapenemase. So these are known as KPC strains. We have other strains of Klebsiella which produce New Delhi metallo-beta-lactamase, NDM1. And among the WHO recognized escape group, so this is Enterococcus, Staphylococcus, Klebsiella, Acineta, Pseudomonas, Enterobacter. These are rated as their priority pathogens for research and development to develop new antibiotics, because all our current antibiotics are failing. And we have numerous studies with all of these pathogens showing that they will survive days or weeks on various surfaces in a dry state, and the outbreaks of the beta-lactamase strains suggest that environmental transmission is very important. So with the superbugs, the newspapers are now full of these reports. So in this one, superbug kills 17 people. This was in a hospital in Manchester, and hundreds have been infected. This was Klebsiella pneumoniae. Now, you know it's serious when politicians get involved. This is the former British Prime Minister, David Cameron, and he, in 2014, said bacteria could become resistant to antibiotics, taking the UK back to the Dark Ages. Politicians starting to wake up to this problem. It's incredible. This is the former Chancellor of the Exchequer. So this is the person who gives out all of the money. So he takes your taxes and then he gives it back out again. And he said, unless we take global action, antimicrobial resistance will become an even greater threat to mankind than cancer. And this followed reviews where they estimated that antimicrobial resistance is going to kill 10 million people by 2050. So this is one person every 3 seconds, and it's going to cost the world $100 trillion. And this is why economists are now very concerned. Now, the WHO have published a lot of literature on the causes of antibiotic resistance. So, for example, doctors prescribe the wrong antibiotics, for example. But very importantly are these two boxes down here: poor infection control in hospitals and clinics, and lack of hygiene and poor sanitation. So these are clearly recognized by WHO. So why do we have an interest in copper? Well, copper has been known since antiquity. It's been used by ancient civilizations for probably 7,000 years that we know of. In ancient Egypt, this is the Egyptian ankh. It's also the symbol for eternal life and also for copper. So the Egyptians linked copper to eternal life. This is the Chinese kanji symbol for the flow of qi, which is life energy. It's also the symbol for copper. This is in ancient medieval Europe, the alchemists. This was their sign, the planetary symbol for Venus, which protects against evil. It's also the symbol for copper. So copper has been well recognized for thousands of years. So for example, in ancient Egypt, 2,000 years ago, they sterilized drinking water, and in fact, when Egyptian soldiers went into battle, they had bronze swords, and after the battle, they sharpened the edge of the sword, and the filings they put into their wounds, and this accelerated wound healing. In Greece, Hippocrates treated leg ulcers and varicose veins with copper. The Aztecs used copper oxide and malachite for skin conditions. Very importantly, in France, particularly in Paris in 1850, they had several outbreaks of cholera in the city. The only group who were protected were the copper workers. It's an interesting association. There was a study done in 1983 by Dr. Phyllis Kuhn, who was a physician in Philadelphia in the USA, and she got some students to swab touch surfaces in her hospital. Now back then they actually still had copper and brass in the hospital, and she noticed they had lower numbers on copper and brass compared to newer materials, and she wrote to a medical journal, presented the data and warned people it was very dangerous to remove copper alloys from healthcare environments, but everyone ignored her. And then in India, for 5,000 years or more, they practice Ayurveda medicine. And part of that is that they use tamra jal here. This is the practice of putting water into a copper or brass container the night before. You wait until the next morning and then you drink the water. And this is very beneficial for you, and they've done microbiology studies, and the water in these copper containers, all the pathogens are being killed. Now, just a little chemistry. Why is copper so good? Here's the periodic table. You will see copper is in this part of the table, and it's above silver and gold. In fact, copper is much more reactive than silver and gold, and this is because if we look at the electron shell of the atom, it has a free electron, which is very unusual for a metal. And what this means is it can donate that electron very easily, for example, to a bacterial cell wall. And this means it can take part in redox reactions and go very quickly from copper to copper 1 to copper 2. So in my lab, we have spent over 20 years now looking at the antimicrobial effects of copper. For example, waterborne pathogens such as Legionella and Helicobacter in drinking water biofilms. We also looked at E. coli 0157 because this had caused outbreaks, particularly in Canada. We then moved on to look at foodborne pathogens, 0157, Salmonella and Listeria. But today I want to focus my talk on hospital-acquired pathogens, MRSA, VRE for example, and also I'll show you some of the work we've done on viruses. There's no time today to discuss the fungi, but I can discuss that later if you wish. So first of all, we wanted to develop a laboratory model. So we wanted to simulate what we call a wet contact. And this is because when you cough or sneeze, you release millions of particles which land on a surface. If you flush a toilet, if the lid is open, you generate an aerosol, and this can move over onto adjacent surfaces. So in this model, we inoculate coupons of different materials, and we add 20 microliters of a bacterial culture, and we spread it out, and then we look to see if bacteria survive on the surfaces or not. Now, when you put, for example, MRSA onto stainless steel, they survive very well. If you put them onto silver, they survive very well. And this is because silver only works when it's ionized in the wet form. It does not work in the dry, despite some of the claims that have been made. Now, importantly, when you put MRSA into copper, now we get a rapid kill. This is log 7 kill within about 40 minutes. And when we put it onto brass, which is 70% copper, 30% zinc, then we still get the log 7 kill, but it takes longer. And then other alloys, as the copper concentration is reduced, takes longer to have the effect. Now, I mentioned Clostridium difficile, and the problem with this pathogen, it forms these spores, and these spores are very tough, very resilient. But if you put them onto copper, and we start off here between log 5 and log 6, then it takes a long time, but over 24 hours, we will get a complete kill. And this is looking at spores, so this is not naked bacteria, it's a tough spore. So in fact, these data, I think, are very impressive. Influenza virus. Every year, it's a problem. And vaccination rates are not that good. And in fact, the vaccine does not work for many patients. So what are the alternatives? Well, one of them is to look at an antiviral surface. So when we put influenza A onto stainless steel, we can incubate it, then recover it, and plate onto a cell culture medium and look to see if particles of virus will grow in the cell culture. And therefore, we can identify the number of survivors. So this is influenza virus after 6 hours on stainless steel and after 24 hours on stainless steel. And we only get a 0.6 log reduction in the viral concentration. Now, when we repeat that on copper, this is 1 hour on copper, we get a 75% reduction in the number of viruses, and after 6 hours, we get over a 4 log reduction. So rapid inactivation compared to stainless steel. Now, I mentioned that many studies have been done looking at survival of these pathogens in a dry state. So here's some data which is in the literature showing MRSA will survive for up to a year, Enterococcus for up to 4 years, Acinetobacter up to a year. So you'll see many of these are surviving for many, many months in a dry state. So they're going to hang around. So we then went on to look at the dry touch surface model, simulating what would happen if you touch a surface with your hand. So to do this, we actually now reduce the concentration, the volume of bacteria from 20 microliters to 1 microliter. And when you spread it out, it dries within just a few seconds. Now, when we look at norovirus, this is the winter vomiting virus, which is very difficult to control in hospitals. And you can see how well it survives. So when we look, for example, at PVC, Teflon, ceramics, we can see survival from log 6 for 2 months. It survives very well. But when we put it onto copper alloys, particularly in the dry model, now we get complete inactivation in 2 or 3 minutes. And on copper alloys, such as copper nickel, we get almost as fast a kill. And on some of the other copper alloys, we get this kill, but it takes longer. So what is going on? So we can isolate the nucleic acid, the RNA, from this virus. And when we recover the virus from stainless steel, you can just make out this band of the viral genome. But when we try and recover from copper or brass, there's nothing there. So the RNA has been destroyed. What about the integrity of the virus? So here's a virus on stainless steel, and it's intact. So the virus is surrounded by a hard protein shell, which protects the RNA genome. But when we put it onto copper, it is completely disrupted, and we lose all signs of the virus. So the copper has destroyed the protein capsid coat around the virus. Now, we've also looked at coronavirus, and for those of you who do not know, coronavirus are related to SARS, which was severe acute respiratory syndrome. That was a potential pandemic around the world 10 years ago. And it's also related to MERS, which is Middle East respiratory syndrome. So if you go to Saudi Arabia, do not touch camels, because camels are a reservoir for MERS, and it is spread in hospital environments. So we repeated the work on non-copper surfaces, and again you'll see very good survival of 4 to 5 days on Teflon, PVC, ceramic, glass, silicone, rubber, and stainless steel. But if we put it onto copper, this is using the moist model, where we're simulating a cough or a sneeze, and you can see we get complete inactivation in 20 minutes for some of the alloys. And again, copper nickel is particularly good for this. And in the dry, simulating just hand transfer, now we get complete inactivation in 2 or 3 minutes for copper and copper nickel, and for brass, a little longer, about 5 minutes. If we look at stainless steel, we get very good survival going on for days. If we look at the virus integrity, this is an intact virus down here. But if you look up here, the virus is starting to disintegrate. So just like the norovirus, copper is destroying the capsid that surrounds this virus. We then went on to look at bacteria such as E. coli and Salmonella typhimurium. They're common in the food industry, but they're becoming more and more common in hospital disease, particularly the E. coli. And again, when we actually look in the dry contact model, the touch surface model, for the E. coli, we're getting complete inactivation in 10 minutes on copper, 20 minutes on brass. And for the Salmonella, now we get even faster kill, 5 minutes on copper and 30 minutes on the brass. Now, it's important to look at these because I mentioned at the start of my talk about antimicrobial resistance. And this is because when Alexander Fleming discovered penicillins, this is the structure of penicillin. And the key structure is this ring, the lactam ring. And bacteria rapidly evolved enzymes to destroy, hydrolyze that ring, the beta-lactamases. So the pharmaceutical industry brought out new variants such as cephalosporins, and bacteria evolved their beta-lactamases, particularly the extended spectrum beta-lactamases, to again hydrolyze that ring. So for example, cefoxitin, which was an antibiotic of choice for quite a few years, we now get widespread resistance. We now more recently have relied on the carbapenems, such as meropenem, but again, bacteria have evolved. They can destroy the carbapenem lactam structure, and this is caused by the KPC, the carbapenemase, and NDM1. And NDM1 was first identified from New Delhi. It was actually a Swedish patient who'd been to New Delhi on holiday, went home, and developed a serious infection. And this was the first report of resistance to the carbapenems. It spread rapidly around the world, probably jet travel. So what happens with these? When we actually put them, so this is the E. coli, cefoxitin resistant, and there's the Klebsiella pneumoniae, New Delhi metallolactamase, and you'll see they survive. This is 40 days on stainless steel. So they survive very, very well. When we put them onto copper, we get complete kill of the cefoxitin-resistant E. coli in 10 minutes, and on brass, it takes about 30 minutes. Now, what's going on? So again, we can actually look at the genes involved in resistance. So here, we've been measuring the carfoxetine resistant gene using the PCR reaction. And you can see this is the gene copy number on stainless steel. So we have 3 to 4 copies per cell on stainless steel for several hours or days. But as soon as we put onto copper, there's 1 hour, there's 2 hours. So the carfoxetine gene is being destroyed. So this immediately asked us the question, what happens when we touch a surface and another bacterium comes and also touches the surface? So you can do a mating experiment. So you can have the antibiotic resistance donors, the carfoxetine or the meropenem resistant bacteria. You can put them onto a surface. You can then put a sensitive recipient, in this case E. coli, onto the surface, mix them together, and then see if you can get transfer of resistance genes to this E. coli recipient. And the answer is yes. So if you do this experiment in a standard lab culture medium, we get very good gene transfer, perhaps not surprisingly. Put them onto stainless steel, even within 2 hours, we're getting very good transfer. So this is dry. We put bacteria onto a dry surface and we're seeing gene transfer. But if we put them onto copper, it's immediately abolished and we get no gene transfer. Now this is really important because if you think someone could fly into Madrid, for example, from Brazil, and if they have not washed their hands, having been to the toilet, they will then touch surfaces in the airport. Someone else can fly into Madrid from, say, Asia, and if they have not washed their hands, touch the same surface, you've introduced 2 different bacteria from different parts of the world. There is now a high risk of creating a new superbug. It's as simple as that. So copper prevents the gene transfer from the resistant bacterium to the recipient bacteria. It stops that process. Again, we can look at the New Delhi metallolactamase strain, which is resistant to meropenem. We get the same results. You put it onto copper, it's completely killed in 5 minutes. Brass, 10 minutes, and some of the other copper alloys between 10 and 15 minutes. Do that gene transfer experiment again, and this is gene transfer of meropenem resistance on stainless steel. You'll see it's very high, but on copper, it's completely abolished. So copper prevents carfoxetine gene resistance transfer and meropenem resistance transfer. So what actually goes on the physiology of bacteria? And this is really important because if all we do is rely on culture, I'm afraid this tells us nothing now because we realize we can stress bacteria and they can become what is called viable but non-culturable, VBNC. It is not sufficient to rely on culture on agar media, for example. You have to do other tests. So we have developed a toolbox of biochemical and physiological tests. Now in these tests, we're taking VRE, so this is vancomycin-resistant enterococci, and we've put them onto stainless steel, and we've stained their DNA with a green fluorescent stain, Cyto 9. And you can see that they're brightly fluorescent. They've got lots of DNA. We can also measure, do they respire? So, and to do this, we use another fluorophore, CTC. CTC does not fluoresce unless bacteria respire and pass electrons to CTC. This becomes reduced and fluoresces red. So when we see red bacteria, they are respiring. So on stainless steel, this is after 4 hours. You see, they've got lots of DNA and they're respiring, metabolizing very well. We put them onto copper. This is 10 minutes. The DNA has gone and the respiration has stopped. So if I just toggle back, you see the immediate difference. We can also measure cell membrane integrity. And what we do, we load bacteria with this fluorophore, rhodamine 123. So in a healthy cell, they take it in and retain it. But if you destroy the cell membrane, the rhodamine leaks back out. So if you have an intact cell, you get bright green fluorescence. If you have a cell which is dead and the membrane has developed holes, they lose fluorescence. And what you will see here, so this column is for stainless steel, and this column is for copper, and this is copper brass. And you'll see for E. coli and also the salmonella that on stainless steel, they keep an intact cell membrane, but on brass, they start to lose it, and on copper, they lose it completely. And this is just a few minutes. Now, here's where there's confusion in the literature, because some people have claimed that copper disrupts the membrane of gram-positive bacteria, such as VRE and MRSA. And the story is not that simple, because while it happens rapidly in gram-negative bacteria, it's much slower in gram-positive bacteria. So copper kills the gram-positive bacteria by inhibiting their respiration and destroying their DNA. The cell wall collapses later, whereas in gram-negative bacteria, the cell wall is attacked very quickly. Now, there's another way to show this. This is Pseudomonas aeruginosa, a very important hospital pathogen. And if we put the Pseudomonas onto stainless steel, you can see we have nice intact cells. If we put them onto copper, you'll see the cells are collapsing, they've ruptured, and they're starting to lose their contents, because copper has caused a lipid peroxidation of the cell membrane, and this forms holes in the cell membrane. So this is how gram-negatives are affected. So what does that mean? In fact, it tells us that bacteria in particular do what we call metabolic suicide. And the reason is, when bacteria land on a copper surface, they liberate copper 1, copper plus. And this, as you've seen, attacks the cell membrane of some bacteria, inhibits the respiration, and destroys the nucleic acid, the DNA and the RNA. But bacteria, when they're alive, produce very small amounts of hydrogen peroxide. And hydrogen peroxide interacts with copper 1 in what is called the Fenton reaction. And this converts copper 1 to copper 2, but very importantly, generates hydroxyl free radical. And this is very powerful and accelerates the copper kill. And this is how we see a relatively slow kill in what we call our wet copper model, and our very rapid kill in the dry copper model. Because in the dry, we're accelerating the Fenton reaction, and we get this accelerated kill. So, conclusions. Contact surfaces are until now an unrecognized reservoir for rapid horizontal gene transfer and emergence of superbugs. Copper alloys kill rapidly, particularly on dry touch surfaces. And the important thing is that copper works continuously, 24 hours a day, 7 days a week. We're getting destruction of genomic and plasmid nucleic acid, and this is very important because this means we're preventing mutation resistance. I'm always re-asked, isn't there a problem? Organisms will become resistant to copper. And the answer is no, because the copper has destroyed their nucleic acid, so they cannot mutate. So we believe a combination of effective cleaning regimes and installation of antimicrobial materials, such as copper, is a very important way forward. So we describe these as an additional infection measure of, by all means, use soap and water to wash your hands, or an alcohol rub, if you prefer, but continue to clean surfaces, but also incorporate antimicrobial copper into the hospital environments. Now, since all of this work first started, there have been approved tests which have been done in test houses, and the copper industry in the USA have registered over 400 copper alloys with the US Environmental Protection Agency. And these have been allowed to use this antimicrobial copper symbol, Cu+. And of course, Copper alloys are now being deployed all over the world, and an economic study has been done by the University of York, and they said if you take into account the number of bed days saved, the reduced mortality and morbidity rates, if you were to build a new hospital in copper, the payback is under 3 months. And in fact, even if you just refurbish in copper and replace all of the stainless steel, aluminium, plastic, the payback is still very rapid. So copper reduces bioburden, and we're going to hear from other speakers during this morning how it reduces infection and saves lives. So you'll hear about intervention studies looking at different copper alloys. Our first speaker has already started to describe these, and there are many studies going on around the world, which I think Michael Schmidt will address in his talk. So finally, I'd like to acknowledge many people in my lab who've been involved in this work, and also Harold Michaels from the Copper Development Association in New York, who has helped us tremendously in this, not least because Harold is a very good metallurgist. So, muchas gracias.